Hello again everyone, welcome back to ptet.chemistry channel. My name is Dr. Art. In this tutorial video, this is an end of year assessment paper based on the Cambridge International O-Level curriculum, which is entirely suitable as well for any 14 to 16 years old students doing the IGCSE or the GCSE triple sciences pure chemistry curriculum. And as per the new syllabus that's coming out and being assessed for the first time in 2023, so basically we have a new 1 hour 45 minutes paper for the Cambridge International O-Level. So these are theory level questions with no choice at all between the questions. It included every single topic in these 14 to 16 years old general chemistry, pure chemistry curriculum, except for environmental chemistry. So this paper excludes environmental chemistry as well as all of organic chemistry. But every other topic you will find will have been assessed in this particular assessment in one way or another after 2 years out of the 3 years doing this curriculum. In this first question, so carbon is an important element. This exists as carbon-12. We pronounce this as carbon-12. And this is a very important isotope as this is the reference standard for when we defined relative atomic mass as stated in the year 9 syllabus. Candidates or candidate students should be able to define relative atomic mass as the average mass. These are the average mass. And as stated in the periodic table, right, they told you it's relative atomic mass, average mass of all the isotopes of an element. And this is relative to, or you are comparing it to 1/12 times the mass of one atom. And this reference standard is of carbon-12. That is why this is a very important isotope. There is also carbon-13 isotope. So for this carbon-12 and carbon-13 isotope, we have this number at the bottom, which is basically known as protons or atomic number. This is defined as the number of protons in the nucleus of an atom. So both of these have 6 protons. There's the identity of the element, proton number, atomic number of 6. We also have this number on top there, this 12 and this 13. These are basically what you call the nucleons or the mass number. That basically tells you the number of protons plus or added together with the number of neutrons. So in this international standard, the standard notation is to the far left rather than in the middle as shown in the periodic table. In this particular format, the bigger number minus the smaller number at the bottom will give you the number of neutrons because the mass number, the heavy substances, the heavy particles are the nucleons in the nucleus. They are the protons and the neutrons having the same relative mass. These are atoms, and when we have atom is uncharged. And because your atom is uncharged, the number of protons must be equal to the number of electrons. For the charges, positive charge must cancel out negative charge. Atom is uncharged. So what we have is 6 electrons and 6 electrons because we have 6 protons, 6 electrons, and we have atom overall is uncharged. Now the number of neutrons, as I mentioned, the nucleon number or the mass number, take away the proton number. So 12 minus 6 giving me 6 neutron there. And the other one is 13 minus 6 giving me 7 neutrons. So same number of protons, different number of neutrons. Isotopes are different atoms of the same element with the same number of protons but different number of neutrons, or you can say different nucleon or the mass number. Name 2 forms of the elements which have giant covalent structures. So these are just your diamond and your graphite. So it doesn't matter which way around it is in. But you should know that the structure of diamond is basically carbon bonded to 4 other carbons. And each carbon is again bonded to 4 other carbons like that. Giant covalent structure. In graphite, however, you will have layers of hexagon. So hexagon are 6-membered ring. So I'm trying my best to draw the 6-member ring, and they are continuous network and they have a layered structure where you have this thing called weak van der Waals, and these are between the layers. Very easy to overcome. That's why they are slippery and lubricating. But then we have each carbon only forming 3 covalent bonds, 1, 2, and 3, as each carbon is only bonded to 3 other carbons. So we have 3 electrons on each carbon, and that is why graphite can conduct electricity. We use as an electrode in batteries as well as in electrolysis, which you will learn more in we already learned it a lot more in electrolysis topic, right? We also have many of these strong covalent bonds. Because of the giant covalent structures, we need to break the many strong covalent bonds in order to melt or boil giant covalent structures. None of the questions here are asking your structure and bonding. This is about Avogadro constant. It's the number of particles in 1 mole, 6.02 times 10 to the 23. We are told that we have 22 grams of CO2. So this is mass. So the first thing we do is we convert mass into mole. So mole equal to mass of mR. So that's 22.0 divided by 44. Because if we work out the mR of CO2, that is just 12 plus 16 times 2. This gives me 44. So mass over the mR, this gives me 0.5 mole of CO2. But then we know that in 1 mole, we have 6.02 times 10 to the 23 molecules, because they wanted the molecule. And we have the mole of the molecule. And that is why in 1 mole, we have 6.02 times 10 to the 23. So if I have 1 mole, I have 6.02 times 10 to the 23 molecules. If I have 0.5 mole, how many molecules do I have? It's going to be that multiplied by 0.5 over 1. That is your mathematics and your direct proportion. So key this into the calculator. You will press 6.02 EXP. The EXP button is just next to the answer button on the calculator, and then you press the 23. There's 6.02 times 10 to the 23 multiplied by 0.5. Don't forget to read your calculator correctly. 3.01 times 10 to the 23 molecules there. Part 2, this is about volume. This is volume of gas, and this is in dm cube. And this is a room temperature and pressure. At the bottom of your periodic table, you are told this thing called molar. Molar gas volume is the volume for 1 mole of any gas at room temperature and pressure. So it's the volume. It's the volume for 1 mole of any gas at room temperature and pressure. So really, the mole of CO2 gas based on the volume is the volume of gas divided by the molar volume of gas. Doesn't matter I write M and G or G and M, it still means the exact same thing. This is in dm cube. At the bottom, I have 24 dm cube per mole. If we can do the unit and the mathematics correctly, 6 divided by 24, I get 0.25 mole of the molecule based on the volume. The strategy is the same then. I'm just going to do 1 mole of the molecule is 6.02 times 10 to the 23. So based on the volume of the gas, I would have 0.25 mole. So my direct proportion says that multiplied by 0.5 divided by 0.1. Divided by 1 itself. So it's just 6.02 exp 23 multiplied by 0.25. I get 1.505 times 10 to the 23. Need to be very careful with this because the thing that we have been given, they are all to 3 significant figure. 6.02, if you see this carefully, 1, 2, and 3 significant figures. 22.0 was 1, 2, and 3 significant figures. 6.00, 3 significant figures. My calculator give me 1, 2, 3, and 4. We are being consistent based on the data given in the question. So this is 3 significant figure. Get straight to the point. For only 1 mark, you should be able to do the calculation on the mole ratio. Sorry, not mole ratio. Calculating the mole of the gas based on the volume and the molar volume of the gas from periodic table. Multiply by Avogadro constant to get the number of molecules. That's it really overall for this 6 marks question. In this next question number 8, so Z is a covalent substance. In experiments, you get a pure solid Z and you keep on heating it for 11 minutes. So this is what we call a heating curve. As stated in the states of matter or kinetic particle theory on the changes in the states of matter. So this is how the temperature of samples of pure Z changes. So on our y-axis, these are the temperature. We could see the change of state as these are the flat line here. And we were told that they are started out with pure solid. So this must be solid region. So these are solid region, and then this is the melting point as the solid turns to liquid. And then obviously above that point we don't see another constant line, so it really doesn't turn to a gas so far in this region. So these are still liquid because it keep on continuously increasing without any change in, without any sharp break in order for another constant temperature there. So what is the melting point? The melting point of pure Z, because this is constant, a pure substance melt and boil at a fixed temperature. The unit is there already. If it is not there, you have to put down the unit based on reading the graph itself. So the sample of pure Z begin to boil at 9th minute. So boiling is to do with liquid going to gas. It was boiled for 2 minutes. So it begins to boil at 9th minute. And it was boiled for 2 minutes. So between the 9th minute and the 11th minute, so it was a pure substance. Pure substance Z has a fixed melting point. So there is no reason why it shouldn't have a fixed boiling point between the 9th and the 11th minute. It should just be a constant line between the 9th and the 11th minute. So 11 is there. So if I just draw like that, hopefully you can see that between the 9th minute, 10th and the 11th, between 9th and 11th minute, it started to boil here and it boiled for 2 minutes. So perhaps when I say it's a liquid there, I should really revise my statement as that is now the boiling point. And am I correct? Yep, because they line it up all the way to this temperature and they say it starts to boil here, so the temperature will remain constant at the boiling point of 220 degrees Celsius and the melting point of 80 degrees Celsius there. So what else? The sample of pure Z was continuously heated between the 2nd and the 5th minute. So between the 2nd and the 5th minute, we have this temperature change of 0. There was no temperature change at all from the 2nd to the 5th minute because that is the melting process going on. So no change in temperature. We also know from kinetic particle theory that temperature is a measure of kinetic energy, average kinetic energy of the particles. These are stated in physics as well. So no change in your kinetic energy because no change in the temperature. Instead, what happened in melting depends on the structure and bonding. You're actually putting in the energy not to make the particle move faster, but for the particles to separate from each other as they go from solid state to the liquid state. Therefore, depending on the structure, you have to break different kind of stuff. In terms of the attractive forces, and you were told that it was a covalent solid, covalent substance. This is info given. But looking at the melting point, 80 degrees Celsius are considered low melting point. 220 degrees Celsius is considered low boiling point. So based on the data, so see the graph, you will see that this one has low melting point and boiling point, suggesting that this one must have simple covalent structure, or you can say simple molecular structure. So what can we say? Why there was no increase in temperature? We know that that was to do with melting. So first of all, we can say that Z must have a simple covalent structure. So this was based on the first information. It was a covalent substance. It has low melting and boiling point. So based on the structure, we can talk about the bonding then. So therefore, melting Z between the 2nd and the 5th minute. Basically only needs very little energy. Is that what they're asking though? Only need very little energy to break the weak intermolecular forces. Intermolecular forces of attractions between the molecule. So what happened there is that doesn't require a lot of energy. Why there was no increase in temperature? Well, precisely because the temperature that we supplied, the heat that we supplied, so this was melting. So the particles are moving further apart. So particles move further apart with no change in speed at all. So no change in speed. Therefore, no change in kinetic energy, no change in temperature at all. So you might be able to skip the covalent structure and just say that melting just requires a small amount of energy, as you are just moving the particles further apart. That is overcoming the intermolecular forces for this simple covalent structure based on the low melting point and the low boiling point, and being told it was covalent substance, it must be a simple covalent structure. Having said that, as with any melting, we are putting in the energy not to change the speed, but to move the particles, in this case the molecules, simple covalent molecule, further and further apart with no change in speed. With no change in speed means no change in your average kinetic energy, and therefore, the temperature remain constant, as temperature is a measure of your average kinetic energy. Somewhere along that line, we have gotten you the 2 marks as well. In part D, describe how the motion of particles, or POZ, change from the 0 minute to the second minute. So from the 0 minute to the second minute, the temperature keep on increasing. Temperature is a measure of your average kinetic energy of the particles. Haven't melted yet, still solid, so they are vibrating about their fixed position. But since the temperature is increasing, therefore the kinetic energy is increasing, therefore they must be vibrating about their fixed position faster, but they are not moving further apart since they haven't reached the melting stage yet. So from the 0 to the second minute, so from the 0 to the second minute, so the particles only vibrate about fixed positions. Only vibrate about fixed positions as they are still solid. As they are still in the solid state. However, what we can comment is they will move faster. They move faster, or they vibrate faster. That's probably a better word. They vibrate faster as temperature increases, since the average kinetic energy also increases. That is all based on kinetic particle theory, which basically says that temperature is a measure of average kinetic energy. They are not moving further apart. The question is not asking on separation. Separation of particles, they are still tightly packed, very tightly packed. They still only vibrate about fixed position, but they are vibrating a lot faster, only until they reach the melting point. Then they start to melt. Then they are not vibrating any faster anymore. Their speed will remain constant because no change in kinetic energy, as there is no change in temperature, as that heat that you supply, the heat energy that you supply, is then used to break the weak intermolecular forces of attraction between the molecules. Because you have a simple covalent structure, melting point, boiling point is to do with structure and also bonding. In part F, the experiment was repeated using a solid sample of impure Z, so no longer pure. Okay, it's a mixture now. So what will happen to the melting point and the boiling point? We know that impurities will lower the melting point, whereas impurities would increase the boiling point. Think about your salt and your pasta. Your salt and boiling water, actually, when you want to cook pasta. So this is to cook pasta. So we add some salt to the boiling water to make it boil at a high temperature so that the pasta will cook a little bit faster. Whereas with the melting point, it was to do with ice and salt, and that will help it to lower the melting point of ice. And this is very important in countries like countries that have winter and they have frost. When you have ice forming on the road surface, it's very dangerous because on an icy surface, your tire, whatever, wouldn't work that well at all due to the friction not being available on the normal road. So what happens is they sprinkle salt like NaCl salt onto ice, and they will lower the melting point such that at 0 degrees Celsius the ice will melt because it will only freeze at a much lower temperature. So impurities lower melting point, impurities make the boiling point higher. So suggest the differences, if any. So the melting point will be lower, but the boiling point will be higher in the presence of impurities compared to the sample of pure Z there. So what we have in a sample of pure Z, when we allow it to cool, so this is kind of like the opposite to heating curve. This is a cooling curve. And we are going to go from 120 degrees Celsius to 20 degrees Celsius. Total time taken was only 8 minutes, starting from the point X, which they have marked at 120 degrees Celsius. And we are cooling it down. So if we think about cooling it down, 120 degrees Celsius was here. So 120 degrees Celsius cooling down will be going down. The melting point is at 80 degrees Celsius. If the melting point is at 80 degrees Celsius, that means that, you know, the freezing point would also be the same as the melting point, which is 80 degrees Celsius. And the total time taken was 8 minutes. It was allowed to cool. How the temperature change? It was allowed to cool to 20 degrees Celsius. So it must be 20 degrees Celsius by the 8 minutes. And I must have my melting point at 80 degrees Celsius. So I guess it doesn't matter if you have it cooling here at the first minute when it cool all the way down, or you could have it cool a little bit slower like that, or you could have it cool a little bit slower like that, but they must come down, and then they will go to a constant line, and then they will come down again. As for how long does it take? How long does it take to cool depends on the previous graph. If we see here, second to the 5th minute, so there is 1, 2, and 3 minutes. 3 minutes for the entire melting. 3 minutes for the entire melting. So there's your first point. Your second point is 3 minutes for melting. Therefore, we are doing the opposite. We are also thinking about 3 minutes for the freezing process, as that was what was shown earlier. So if I had it here, 3 and 3 should give me to 6, and that will be all right. If I go all the way to 6 here, 6 and 3 minutes would exceed 8 minutes, and you only had this total time taken was 8 minutes. So you could have chosen any of these 3. Really doesn't matter which one you choose. And then I'm just going to put in the 3 extra minutes, 2 to 5 perhaps. So 2 to 5. And I guess probably I should look at 120 to 80. 120 to 80, 80 to 120 takes around, how much time, yeah? Around 1 minute only, so 5th to the 6th minute. So only take 1 minute to go from 80 to 120. So perhaps I should really follow the graph, give or take around 1 minute and around 1.2 minutes. If I really want to be super accurate, I should probably follow that. How much time did I say it had just now? From this 80 to 120, it was 1.2. So 1.2 would be there. Okay, so from 80 to 120 degrees Celsius from the previous graph was around 1.2 minutes. So I'm cooling in 1.2 minutes all the way to 80. And then what I had is 3 minutes, so give or take 3 minutes. This is a bit tricky. I don't want to be super exact, but 1, 2, 3, so perhaps around that region there, around 5.2 since I started from here. So it doesn't need to be super exact. I guess you'll probably be forgiven if you had 2 to 5, and that will be alright. And then the next bit of the graph is just cool all the way. I think what is most important is you must have the freezing point at 80 degrees Celsius. You must have it like over 3 minutes, and you must have it coming down, constant coming down, everything finishing at 8 minutes. That should have given you the full 2 marks, and that should give you the 9 marks overall for this question there. So in this particular question, this is about electrolysis. We know electrolysis is basically passing electrical current through electrolyte in order to, decompose or break down the electrolyte into the respective elements. So what is meant by electrolyte, not electrolysis. So be very careful about the process and the required material that we need for electrolysis. This is electrolyte, so this must be electrolyte must be molten or aqueous ionic compounds, because we are referring to compounds that consist of ions, and that's why we can separate them into the cations and anions, and they'll be attracted to the cathode and anode respectively. So they must be molten in the liquid state, or they must be dissolved in water in order for electricity to pass through, or electrical current to pass through or to conduct, because your ions are not free to move in the solid state, as they can only vibrate about fixed positions in the giant ionic lattice structure in the solid state. And when they are molten or aqueous state, then the ions become free to move, and this is required for the electrical current to pass through or to conduct in order to break them down, and breaking them down and break it down into the respective elements that made up the ions. So this is basically kind of like relating electrolysis to what is the electrolyte itself. For the 1 mark, you really have to talk about the molten or the aqueous ionic compounds in order for the electricity to conduct. Don't really need the second point, I guess. So if you don't have the second point, it is entirely fine, but you should really have the first point there, molten or aqueous ionic compound. In part B, this table gives us information about the electrolysis of two electrolytes. We have used graphite consisting of layers of carbon atoms, but then there are free electrons on each carbon, because you only uses 3 out of 4 electrons in the outer shell for forming covalent bonds, since you only form 3 covalent bonds to the other carbon atoms, hexagonal layers upon layers with weak van der Waals forces between the layers. Nonetheless, we have this electrolyte. This is aqueous. Aqueous would mean you have H plus and OH minus, and then you have copper 2 sulfate, Cu2 plus, SO4 2 minus. These are ions that are in the qualitative analysis as part of experimental techniques and chemical analysis topic in year 9. These are also in practical studies, copper 2 plus, SO4 2 minus, OH minus, and H plus. And then we see at the anode, we know that anode attract anions. So anions are negatively charged. This makes anode positively charged. Anions get attracted to anode, and then cations get attracted to cathode. We know cations are positively charged. This means cathode are negatively charged. We also know that reduction happens at cathode. So red cat would mean that reduction happens at cathode. And we also know about oil rig acronym, and oil rig acronym basically says that reduction involves the gain of electrons. So this must be oil rig there. So reduction is gain of electrons at the cathode by the cations. So we see colorless bubbles. These are colorless and these are bubbles. Bubbles represent gases. Why in the world do we get the gas here? Typically, we would say that copper 2 plus would prefer to be, reduced. Hang on, this is anode actually. So we don't say that at the anode. At the anode is the anion between the hydroxide and the sulfate. So really, we are looking at the hydroxide being oxidized at the anode. So oxidation is loss of electrons. This is the anion losing electrons at the anode. That's where the anion are going. You get a colorless bubbles, because that is essentially the OH minus becoming the oxygen gas, and you get H2O, which was already present to begin with, because these are all in aqueous solution. So your product is not H2O, it's actually O2. And balancing our equation, we must have 2 H2O, 4 OH minus. We are losing electrons. OH minus is losing electron. We have the plus electron on the right hand side. This is 4 electrons on the right hand side there. So eventually, this name of product. They don't want the formula. This has got to be oxygen gas. If you write oxygen is fine because oxygen exists as a gas, diatomic oxygen gas. We have constant, well, let's just finish off this one first actually. So at the cathode, our observations, depending on which of H plus or CO2 plus get reduced, has to be copper 2 plus, as copper is below hydrogen in the reactivity series. So we know that copper is less reactive than hydrogen, and therefore copper favor reduction. So the Cu2 plus 2 electrons giving you Cu. We are going to get copper as a solid, not copper 2 ion, but copper as a solid. The observation is you will get a pink solid, or you can also call it red-brown solid. So this solid will form at the cathode there. Now looking at the next one, we have concentrated. So as to do with concentration, and concentration can affect what halide get get oxidized at the anode. So in this case, we have bromide, and we also have the aqueous component. So when you think about concentrated sodium bromide solution, we have Na plus and Br minus. We also have a H plus and OH minus, but because we have concentrated solution, it will favor the halide rather than the OH minus. And between the Na plus and H plus, it will still favor the H plus getting reduced at the cathode, because reduction of the cations that goes to the cathode are the cations getting reduced at the cathode, which involve the cations gaining electrons. The H plus gaining electrons will give you hydrogen gas. So when they give you hydrogen gas like that, we're gonna have 2H plus, and then we're gonna have 2E minus in order for us to balance that equation there. And that is why the product is hydrogen gas. As a result, you see colorless bubbles. How about at the anode? At the anode is the Br minus that get oxidized rather than the OH minus. The Br minus get oxidized to Br2. The Br minus loses the electrons. We count the atoms, 2 Br there. So 2 Br minus, and minus 1 times 2 is minus 2. So I needed 2E minus there. So what do we get? We get bromine, not bromide. Bromine as a molecule, diatomic molecule. But bromine as a group 7 diatomic molecule, it is also colored. So you can say you get a reddish brown liquid, because that is the color of liquid bromine. Reddish brown liquid. But then we also apply electricity through the electrolyte, and these are simple covalent molecule Br2, so it might boil off and give you some sort of brown vapor or brown gas, but the first thing you will notice is a reddish brown liquid before it will go to a brown gas. Looking at the next part, hydrogen is produced at the negative electrode, which is the cathode. It's negatively charged terminal because it attracts cations which are positively charged. Produce hydrogen. And write the ionic equations for this reaction. So they just want the half equation. They also want the ionic equation. This is basically the H plus going to the cathode. Reduction happened at the cathode. Reduction is gain of electrons by the H plus at the cathode, giving you H2 molecule gas there. 2 hydrogen atoms, so 2H plus. No charge on the molecule. There is a charge on the ion. Plus 1 times 2 is plus 2. I needed 2 electrons to balance my equation there from year 9, redox half equation. Now state 2 reasons why this graphite is suitable to use as an electrode. Number 1 is that it is chemically unreactive. And it is inert electrode. Of course, when we produce oxygen at the anode, such as for these aqueous copper to sulfate, also in the electrolysis of Al2O3, when we use this cheap graphite electrode which can conduct electricity, we need to replace the anode consistently, because the carbon, despite it having not much reaction, it does combust with oxygen to give you carbon dioxide, and your carbon electrode will get smaller in size. It's also cheap. It's cheap to replace if needed. So, it's exactly the same material as you have in your pencil. So graphite itself is cheap to replace. If you want to, suitable to use as electrode, it conducts electricity. So if it doesn't conduct electricity, we wouldn't have used it at all. And we don't want to use metals. And this is probably why I put this as reason number 3. So this is not a very good reason, because you could have used any other metal like platinum. But then, of course, graphite is a lot cheaper than platinum, which is a precious metal. So it is a cheap stuff, not just to replace, but also to use on its own as well. It's cheaper than platinum, for instance. That's it really, overall, for this 10 marks question on electrolysis. In this next question, so iron is a transition element in the middle block of the periodic table. Potassium is a group 1 element. You will call this as alkali metal, or alkali metal, I don't know how you pronounce it properly. But iron and potassium have the same type of bonding. We are not talking about structure, we're talking about the bonding. Name the type of bonding. That has got to be metallic bond. There is no such thing as giant metallic bond or simple covalent bond, simple metallic bond, because giant or simple is to do with structure, whereas the bonding is the electrostatic force of attraction. And when they ask you for description, there is nothing better than you drawing a very, very simple diagram to represent the layers of cations. They are of the same sizes. Because they are of the same sizes, they can slide over each other easily. And I would draw in my delocalized valence electrons. And when we draw something, we should always label. These are the C of delocalized valence electrons. They are delocalized from the outer shell of the metal as an atom, because you want to lose the outer shell electrons so that you get a completely filled outer shell. These are the metal cations. So we do not have anions. Instead, what we have, the description of the type of bonding, is that we have a giant metallic lattice structure. Should probably put these further here, for instance, so that we are not confused. And then we have a giant metallic lattice structure. So metals have giant metallic lattice structure. I know we are not being asked for it, but structure and bonding are not something to be messed around with. So they want you to describe what is metallic bond. Metallic bond is basically the strong electrostatic force of attraction. As with any type of bonding, it is always electrostatic in nature. Electrostatic or electrostatic, I don't know how you pronounce it properly, is basically something between positive charge and negative charge. In this case, is between the metal cations, which you get after you lose the outer shell electrons, and your negatively charged valence electrons. So C of delocalized valence electrons, that is your positive and your negatively charged species there. Perhaps I can label it, I can write it out in full there. C of delocalized valence electrons there. Part B, transition elements and group 1 elements have some similar physical properties. Can be hammered into thin shape, can be hammered into any shape. Basically, is a property called malleable. And they conduct electricity. In fact, we know that it is good electrical conductor, and that is due to the presence of the free electrons. So you got the free C of delocalized valence electrons in any giant metallic structure. They are free to move, not the cations, but the electrons are always free to move, even in the solid state. Can be stretched into wires. This is to do with ductile, and this is the very reason why copper, having very high ductility, is very often used as copper wires in all our electrical appliances. Now name the term. Ability of elements to be hammered into thin shape, into any shape. That is basically malleable or malleability. If you want the noun, it's actually malleability. Malleable is the property, is the adjective there. Describe what happens to the particles in iron when it is hammered into a shape. When you apply force onto the giant metallic structures, the layers of cations of the same sizes, they can slide over each other easily. So we can say that the layers of cations all of the same sizes because you only have element, all of the same sizes, since only one element, which is iron, it is not mixed with another metal. They can slide over each other. They slide over each other easily upon application of force, and that is what happened, resulting from its malleability. Now suggest why copper rather than other transition elements is used for wires which conduct electricity. So why don't we use any other transition elements? Suggest why. So well, we can think about copper has high electrical conductivity, and we can also think about other properties as well. So it is very ductile, for instance. Conductivity, very ductile as compared to other metals, which made it really useful to be used for electrical wiring. Perhaps I can talk about ductility rather than electrical conductivity, because that is actually something that is a lot more important in being used as a wiring equipment. We can also say that it's actually not much cheaper. It's actually not much cheaper compared to other metals, but it is so widely used that we generally accept that it's kind of universal in its application of being used as this electrical wiring material. So copper is ductile or high ductility. So that is what made it useful as an electrical wiring kind of metal. The next bit, transition elements are harder and stronger than your group 1 elements. We know that group 1 metals are going to be soft, and they are very soft metal. They are not very hard metal. This is unique to group 1. Describe how two other physical properties are different. So when they say different, you gotta compare and contrast. We can think about the melting point first. So transition metals have high melting point. Transition metals have high melting point, much higher melting point. I can compare straight away, have much higher melting point than group 1 metals, which have low melting point, by the way. So the group 1 metals definitely have a lot lower melting point compared to transition metals. What else can I say? Transition metals or transition elements, they mean the exact same thing, because the transition elements are basically all metals. The transition metals are basically all elements. So the transition metals, other than harder and stronger, they have much higher density, whereas group 1 metals have very low density. Some of them float on water, like lithium, potassium, and sodium. So much higher density than group 1 metals there. And that's it really for that 2 marks questions. Now part D, chemical properties. Just now was about physical properties. This is about chemical properties of some group 1 elements. We know that this is lithium, sodium, potassium, rubidium. So this is down the alkali metals, so down group 1. These are Roman numeral as stated in the periodic table, as also given in the real exam. We gotta specify the flame test color. So lithium, they have given you as the red color. Calcium is actually red orange, but lithium is red in color. These are of the Li+, so it's the flame test of the cation. This is Rb+, the cation give you ruby red. So the Na+ is actually going to be orange yellow. For the Na+, and then the potassium is going to be lilac for the K+ flame test. Now in terms of the reaction with cold water, we know the reactivity down group 1 is going to increase. This is steadily effervescence, strongly effervescence, very strongly effervescence. I would say much stronger effervescence, rapid, very rapid or very strong effervescence. Somewhere along that line should be all right. That means there is a lot of bubble. Effervesces. Better spell that properly. Effervesces. That may form very rapid bubbling, but it also forms colorless solution. So the reaction could be explosive because it can catch on flame, but reaction with oxygen, so this one is very slowly, quickly. I can use the term very quickly forms an oxide layer. So we're just playing around with the words, and we know that reactivity of the group 1 metal would definitely become faster going down group 1 as it becomes easier to lose the outer shell electrons. At the flame test, at the predicted reactions, that should be alright. If it's an explosive reaction, catches on fire, that should be alright as well. Now name the gas. This is group 1 elements. These are basically reactive metal. When you have reactive metal, adding with water, you are supposed to get the metal hydroxide, not the oxide, because we are not dealing with steam, we are dealing with water. So it's forming the metal hydroxide and hydrogen gas. Name the gas. So this is hydrogen as a gas, which is of course having the H2 formula, diatomic molecules, 2 atoms covalently bonded together to give you a molecule. Name the solution when potassium reacts with water. So the potassium hydroxide is going to be soluble in water. Whatever they contain, Na plus or K plus or NH4 plus, everything that contain these ions, they are all soluble in water as part of the solubility rules. Predict the pH of the colorless solution. When potassium reacts with water, they are called alkali metal because potassium hydroxide very soluble. You call it alkaline solution. You also have a strong base as they are very soluble in water. So they dissociate completely in water to give you OH minus. This will be pH 14 or pH 13. That will be acceptable as well. 12 is a bit low already. Now the next one is a reaction of sodium, but this is with oxygen. So they will form an oxide of group 1. So sodium form Na plus ions, O2 minus from the oxygen atom, and this is 1 and 2. These are what you call valency. The combining power of the ions are based on the charges of the ions from year 9 actually. Under chemical formulation, we crisscross as there is primary school mathematics on the lowest common multiple on cancelling out the charges, +1 and +1, cancelling out the -2 of 1 O2 minus. Our formulation is 2 of the Na, 1 of the oxygen, Na2O. Of course, we must balance our equation. There are 2 oxygen atoms. There is only 1 oxygen atoms. So we put a 2 in front. And having done that, we have 4 sodium. So we put 4 sodium in front. Part E, iron is a typical transition element. It is the catalyst used in the Haber process. So what is actually happening in the Haber process? The nitrogen reacting with hydrogen reversibly in order to give you ammonia gas. These are all in the year 9 structure and bonding dot and cross chemical formulation. I put a 2 in front to balance the 2 nitrogen atoms, and then I have 6 hydrogen atoms, which I need to put a 3 there. It's 2 marks there to indicate the balance equation as well as the reversible step, and this is quite a giveaway as they didn't even ask for the stat symbol. But if they do ask for the stat symbol, these are all in the gaseous phase, and your catalyst is a metal, is a finely powdered iron for the maximum surface area of the catalyst for the maximum rate of catalysis as well. The next one is including the units, state the temperature as well as the pressure used for the Haber process. Stated in the syllabus, we use 450 degrees Celsius. We also need very, very high pressure of 200 atm pressure. This 450 degrees Celsius is what you call a compromise temperature, because we know that it's to do with how fast you want high temperature. But then if you want to think about how much NH3 that we want low temperature, as the forward reaction is exothermic, and that means it releases heat energy to the surrounding. When you go too high of a temperature, the equilibrium will try to oppose the change and make it release lesser heat, and you release heat in the forward reactions. So releasing lesser heat would mean you favor backward reactions. So lower temperature would favor forward reaction, higher temperature would favor backward reaction for a exothermic forward reaction. Those are to do with equilibrium, and this is to do with rate of reaction. Of course, at higher temperature, kinetic particle theory says your particle will get more kinetic energy, collide more frequently at a higher speed. Therefore, you get more effective collisions, faster rate of reaction. They contradict. That's why you have to come to compromise. 450 degrees Celsius is stated in the syllabus. Very high pressure, counting the moles of gases on the left, 4 moles of gases on the left, 2 moles of gases on the right. Higher pressure, equilibrium try to lower the pressure by shifting to the side with lesser gaseous molecules. That's to the right, favoring the right hand side. Also faster rate of reaction, as the gas particles will be squeezed closer together and they collide more frequently at higher pressure. Collide more frequently, more effective collisions, faster rate of reactions. That didn't ask you all that, but these are very good and related questions under rate versus equilibrium yield, how much versus how fast. Very classic type of reactions together with Haber or contact or any sort of equilibrium versus rate kind of question. That's it really. Overall for these 21 marks on inorganic chemistry, periodicity, and reactivity of metals. In this question number 5, this student investigated the progress of reactions. This is between an acid and an excess of large pieces. Marble chip is basically calcium carbonate. And we have a gas syringe. Gas syringe will collect volume of gas. And the difference between a gas syringe and a gas jar is that a gas syringe has these graduated lines that can measure the volume of gas. We have a rubber band to prevent the gas from escaping, but these are large pieces of marble which are going to react a bit slower than if you crush the marbles. We have excess of it, so that means the dilute hydrochloric acid is what we call the limiting reactant. Limiting reactant is a year 9 concept. It means it is used up totally. It is used up completely. So a graph of the volume of gas produced against time. This is how much of the gas get produced over time. So the rate of reaction is going to be the change in the volume of gas, the change in amount, which in this case is the volume of gas, over the change in your time. How much it changes over time. This is basically the gradient of the line. The gradient of the line at various time points is going to tell you what is happening to the rate of reaction. When the gradient of this horizontal line, the gradient is going to be 0 because the rate has come to a stop and the reaction has finished at this point, which is 200 seconds. Now state how the shape of the graph shows you that the rate decreases as the reaction progresses. If we see the initial rate, I'm drawing this in the green color of highlighter. You're not allowed highlighter in exam, but it's a lot easier if I show you this. This is called initial rate. I have drawn a tangent. A tangent is a straight line. This is a tangent at time equal to 0. It gives me a gradient of however much y value change divided by the change in the value of x. As we progresses, you can see that the gradient, now the red color lines, the gradient has become less steeper. And if I draw another line for when it becomes horizontal totally, so we can see that gradient at various time point, gradient decreases. And if the gradient decreases over time, so that would mean that lesser and lesser volume of gas get produced over the same time, and therefore rate of reaction decreases. For that 1 mark, how does the shape of the graph? So as time increases on the x-axis, we can see that gradient, the gradient, or you can say steepness of the slope, which is basically the gradient at various time point decreases. It becomes less steep and rate decreases. So therefore, rate decreases or rate becomes slower, etc., etc. Suggests why the rate of reaction decreases as the reaction progresses. We need to be very careful because the question did mention that we have excess of large pieces of marble. You cannot say that the reactants get used up. Well, this is not used up, so we need to be very careful what is actually used up. So not the marble, it is actually the dilute hydrochloric acid that get used up. So as marble is in excess, according to the question, so HCl aqueous is limiting, and then as reaction progresses, more and more of the acid get used up. So more acid get consumed, more acid gets used up. So therefore lesser H plus, or you can say less concentrated acid, therefore lesser collision, less effective collision, or you can say collide less frequently first, because collision theory is to do with collision frequency, and therefore less effective collisions, so rate of reaction is going to go down. Rate of reaction will decrease. There is no point of me repeating the questions, since the question asked me on why rather than repeating the exact same thing in the question there. Deduce the time when the reaction finishes, so the rate becomes 0. So when does the thing become horizontal? So as mentioned just now, not yesterday, it's basically at this point. So we are looking at time equal to 200 seconds. So the unit is on the graph. Reading there, that's when it first become horizontal. So there's 200 seconds there. So 200, they did give us the unit, so we are safe there. But if they don't give us the unit, we must write down the unit there. Part B, this experiment is repeated. Same mass, smaller pieces of marble. All other conditions are kept the same. So these are your control variable because you keep them constant. So no change at all because you are just simply changing the surface area. The smaller pieces of marble will have a larger surface area, and that means the reacting particles have a larger surface area, meaning you have a larger point of contact between the reacting particles that can collide more frequently. And if the reacting particles can collide more frequently, so that means faster rate of reaction. So draw a line on the grid for 2 marks. You are using the same mass of the marble, and because all other conditions are the same, this includes the same concentration and the volume of HCl, which is limiting. And if the HCl is limiting and there is no change in that, you get the same volume of gas. So there is no change in how much you get, but there is a change in the rate. You get it a little bit faster, but you still get the same volume of gas there. So if I just rub out the grid and the other bit, so that we are just labeling one stuff here. So this is our final volume, which is around this 50, 60, 70, 80, 90. I believe this is 90 cm cube. So what I could do is I could just curve up and show that I am a lot faster. So I will end up at 90 a lot earlier compared to this thing which only finishes at 200 seconds. I would have finished at around, I don't know, much lesser because I use smaller pieces and I should label the stuff. What question number was that? That was part B. I get the same volume of gas because I have the exact same mole based on the same concentration and same volume of the limiting reactant. And the surface area, the larger surface area, just make it a lot faster. So this is part B. So you have 2 points here. Faster reactions, if you see the gradient is a lot steeper than that. Faster reaction, but it finishes much earlier, so it's faster also. And it still gives you the same volume of the gas since the mole of the acid are exactly the same there. Part C, the original experiment is repeated at a higher temperature. All other conditions are kept the same. And then we talk about the rate of reaction being able to be explained in terms of activation energy as well as collisions between particles. So this is collision theory. particle must collide with enough energy. So you must have energy greater than or equal to the activation energy. Define the term activation energy as stated in the syllabus. It is the minimum energy required. Minimum energy required or needed. Needed by what? By the reacting particles and before they can react. Before they can undergo a reaction. You can also say that it's the minimum energy needed or minimum energy that the reacting particles need or require before they can react. So explain why the rate of reaction increases when temperature increases in terms of activation energy. Number 1, in terms of collision between particles. Number 2, so we need to think about this energy greater than or equal to EA. We need to think about collision frequency, which is to do with, collision theory. So there are a couple of points here for these 3 marks. So we're going to be thinking about, the first point, at higher temperature or as temperature increases. These are our fixed essay, to be honest. Then we say reacting particles will gain more kinetic energy. As we know that temperature is a measure of your average kinetic energy of the particles. So the particles gain more kinetic energy, they move faster or they collide faster. We can also say that they collide more frequently. So that is to do with frequent collision. So that should be actually number 2. And then when I think about my number 1, so also there will be more particles. They would have gain energy. There are more particles with enough energy or with energy greater than or equal to the activation energy. So therefore, there are more effective collisions, because effective collision simply says that you must overcome the activation energy in order for the reaction to happen. So overall, due to, greater collision frequency and also more effective collision as a result of more particles having energy greater than or equal to EA, as your particles did gain energy, and therefore overall rate of reaction increases. Well, actually, you don't get extra mark for this last point because they are just asking you why the rate of reaction increases. I have just completed the essay. There is no extra mark here because it was already mentioned in the question. It wasn't like, what happened to the rate and explain it. It was like explained why that is the case. So there is no extra mark there. That's it really overall for these 9 marks questions on rate of reaction, kinetic particle theory, collision theory, activation energy. Question number 6, ethanoic acid is a weak acid. We know a weak acid for ethanoic acid is probably pH 5, pH 6 like that. Hydrochloric acid is a strong acid, so pH 1 or pH 2 are acceptable. But they don't ask for weak or strong acid, they just ask for the simple generic term. Acid is a substance that dissociates in water. If you don't like the word dissociate, you can say ionizes, but we ionize in water. What do we produce? What do we form? What do we give? We give a hydrogen ion, which is H plus, present in every single acid. The thing with strong acid is that you will get a full dissociation, such as HCl going to H plus and Cl minus, full dissociation with a full headed arrow, strong acid, full dissociation to H plus in water. A weak acid dissociate partially, and that is essentially, actually that is already given there. Complete the equation to show the changes which occur when the weak acid is added to water. So we talk about the partial dissociation. So we say that we know it partially dissociates, or if you want, you can use the word partially ionizes, and this will form H plus ions in solution or in water. Basically, it means the same thing. In water, in solution, dissolve in water to give you a solution. So what we do is we use a reversible arrow to show the partial dissociation, and then we will get H plus The H plus comes from there, and since they have given us that symbol, we should really put in the stat symbol as well just to be consistent. If the H plus come from there, I will have a -1 charge for the remaining part of the molecule, giving me everything the same, but without the H, without the plus, I must be minus, and this must be aqueous. These are in the case study under weak acid, reversible dissociation, partial dissociation into H plus in solution from the weak acid, and the pH is a lot higher, pH 5, pH 6. This is ethanoic acid. Ethanoic acid is a component of vinegar, and we will learn more about it in a year 11th organic chemistry topic on carboxylic acid, although this was already in the syllabus under acid, bases, and salt. In this question number 11, hydrochloric acid produces salts that you call chlorides. So you have magnesium carbonate. All carbonates are insoluble. So all carbonate salts are insoluble except for the 3 cations that make every salt soluble, Na+, K+, as well as NH4+. These are in the solubility rules of salts. We are given the equation where 1 mole of MgCO3 reacting with 2 mole of it, giving us magnesium chloride. As we know, Mg2+, Cl-, 2 and 1 based on the valency, which is the combining power based on the charges of the ions. This is how many of these ions you need as you do the lowest common multiple, how many of the ions combine together for the charge to cancel out. And we also get carbon dioxide, as there is the test for carbonate in the qualitative analysis. Add any acid, reacting with any carbonate, giving you effervescence, a lot of bubbles, and you test for this gas by bubbling the gas into lime water, and the lime water will turn milky. So this student used 50.00 cm cube, very accurate volume, very accurate volume. So it's impossible that you do this by using measuring cylinder. It has to be by using a burette, so B-U-R-E-T-T-E there. And this is particular concentration of hydrochloric acid to give you a magnesium chloride. Calculate the mass of magnesium carbonate. So this is to do with reacting masses. So we want this, but we have the HCl. So calculate the moles of HCl present in this particular volume, in this particular concentration. These are what we call solution chemistry. So N equal to C times V. So the C is 2.00 mole per dm cube, but the volume there is in cm cube. So that is 50.00 dividing by 1,000, which, if you have done normal mathematics before, this is actually times 10 to the minus 3 means 50.00 dividing by 1,000. You press this on the calculator by pressing 50.00 EXP button next to the calculator, and then press the minus 3 there. So me doing that, and I get 0.1. Calculator does not tell me how many significant figures, but we know, looking at the question, 2.00, there's 3 significant figures. 50.00, there's 4 significant figures. If I'm to be consistent, I always go with the lowest significant figure in the data given. So I will add in the significant figures. This is 3 significant figure, mole per dm cube multiplied by the volume in dm cube there. So consistent number of significant figures. Determine the moles of MgCO3. So you want the moles, not the mass, first of all. So we look at the mole ratio. So the mole of the MgCO3 is to the mole of the HCl from the balance equation. We have 1 mole of MgCO3, so we put 1 on top. We have 2 moles of HCl at the bottom, we put 2 at the bottom. On the top there, this is the actual mole of MgCO3 we want, and we have the mole of HCl at the bottom there. So what I'm going to do is make the actual mole of MgCO3 the subject. So the actual mole of MgCO3 is equal to 1/2 times 0.100. Should perhaps move my working a little bit to one side so that I would have enough space there. So my previous answer divided by 2. Again, 3 significant figures consistent with the data accuracy in the question as given earlier. Now calculate the relative formula mass, which is Mr. So we know the mole of MgCO3 which was equal to 0.0500. That's to do with the mass over the MR. Do we know the mass? We are told that we react, we don't know. We actually don't know the mass yet, so we're just calculating the MR. So I guess we can just use our periodic table. MR of MgCO3, that is 24 plus 12 plus 16 times 3. Summing up the relative atomic masses in from your periodic table, giving us 84. And I think last but not least, I'm supposed to link the MR and the mole of the MgCO3. So the mole equal to mass over the MR. So the mass is going to be the mole multiplied by the MR. We have the mole of 0.0500. We have the MR of 84. So pressing that into your calculator, and you get 4.2 gram. So this is the mass. Well, should be rounded up to 3 significant figures, such that you get 1, 2, and 3 significant figures. Because calculator counting on your behalf, we have maintained the consistency of 3 significant figures based on the accuracy in the data. This is straight from periodic table, so we can't change anything at all. But these were 3, 3, and 3 significant figures, and that's it really for this 4 marks question, which I think get continued. Yes, there is continuation to this question. In this part D, so this student prepare crystals of magnesium chloride. You use excess of this magnesium carbonate because this is insoluble. So we can remove these by filtration later on. When we filter the mixture, why do you add excess of magnesium carbonate? So MgCO3 of magnesium carbonate is insoluble. So we want to make certain that all the acid get used up. So all the HCl gets consumed, all reacted, get used up, consumed, all reacted, because it's difficult to get rid of solutions, but it's very easy to get rid of the solid, which is insoluble. Why does the student rinse the residue? The stuff we want is actually soluble, that's why we can crystallize it. Crystallization, you obtain the solid from the soluble salt itself from the solution. So this is to wash off any soluble salt that we produce, that we form. So you are forming the magnesium chloride solution, which is soluble, and some of them may be stuck onto the magnesium carbonate residue. So you want to wash off and ensure as much of it is collected as possible. This next bit is basically how would you obtain pure crystals. They didn't ask on dry crystals, but they want pure and they want crystals. So crystals is 1 mark, pure is another 1 mark. Usually if they ask for pure dry crystals, you will get another 3rd mark for dry, but I guess 3 marks is pretty generous here. From the filtrate is the liquid that passes through the filter paper. So what we do is we heat the filtrate. We heat the filtrate in an evaporating dish, and we heat it until it is saturated. Saturated meaning it's got the maximum amount of solute dissolved in a fixed amount of solvent at a particular temperature, and then we leave the saturated solution to cool. So it is a solution with no solid whatsoever. As we leave it to cool, and crystals will form. As you form the crystals are solid. Then filter the crystals. We filter the crystals and we gotta wash it in order to purify it, and wash it with distilled water, because we don't wash with just any water. We wash it with cold distilled water. They didn't ask for drying, but then usually what we do is we would dry the crystals in between filter papers. These are the key concept for crystallization assay that started out with heating until saturated solution, leaving the solution to cool, and crystals will form as it cools down. And then we'll filter, we wash, and then we dry the crystals in between filter paper, just like that. You get 3 mark crystallization assay. So the next part, we have silver chloride. We know about the solubility rules. These are the solubility rules for the chloride, and also from the test for chloride by adding nitric acid, and then we added some aqueous silver nitrate. We get a white precipitate. Silver chloride is insoluble, therefore we can make it by precipitation reaction. This is between aqueous barium chloride, so that is a solution, and then we take another suitable aqueous silver salt. It needs to be soluble as well for this particular aqueous salt. You got to choose an anion to make it suitable. So we know about all nitrate salt are going to be soluble, so we always go for the nitrate salt that will be soluble given the cation here. What is meant by the term precipitate? So basically it means insoluble solid. You cannot see through, it is not a solution. The next bit is name a suitable silver salt. It's got to be a salt. It cannot be a silver oxide or something. It's got to be silver nitrate. All nitrates are soluble. And what can we do? We can then write the formation of insoluble silver chloride from the aqueous barium chloride. They want the chemical equation. They don't want the ionic equation, because the ionic equation would have been much easier to write. There would have been the Cl minus plus the Ag plus, giving you the AgCl solid, which is insoluble. That is your classic ionic equation for the precipitation reaction of this insoluble salt. Aqueous solution and aqueous solution come together to give you this insoluble white precipitate. You wanted the full balance equation, silver nitrate, Ag plus NO3 minus, giving you plus 1 and minus 1, one of each. They're going to give you the AgCl precipitate, and when they exchange the partners, they will give you barium nitrate. We know that all nitrates are soluble. We also know that barium being a group 2 ions, as you have done this in the flame test of barium 2+, giving you a light green kind of flame. Group 2 giving you +2 charge, nitrate giving you a -1 charge. When we exchange the valency, that means we have one of these barium 2+ and two of these NO3 minus, such that we use a bracket for their formulation. 2 of the -1 cancel out the charge of the +2, barium nitrate. All nitrate is soluble. They haven't asked for the stat symbol. You don't get extra mark for the stat symbol. All nitrates are soluble again. And this is barium chloride, which is soluble. As we know, all chlorides are soluble except for silver chloride and also lead 2 chloride according to the syllabus. So barium chloride, aqueous barium chloride is soluble there. So they just wanted the full balance equation. Of course, we cannot go away until we have balanced it. We got 2 chloride there, so we need to have 2 Cl there. Having done that, I've got 2 Ag, so I put 2 in front of the AgNO3. I've got 2 of the NO3 unit. I've got 2 of the NO3 unit. These are called balance equations. Even when they don't ask you to balance, you must write balance chemical equation. And that's it really for this 3 marks question. And that's it really overall for this 16 marks. Really long question there. Question 7, this question is about ethanol. So we know this is ethanol. It comes from a family which is related to methanol, which are definitely alcohols. Alcohols are flammable. Methanol is in the year 9 dot and cross for the covalent bond under simple covalent molecule. And that was part of the syllabus as the name there. Well, ethanol is this. It's got 2 carbons instead of 1 carbon, CH3OH for methanol. It's got oxygen. These have been drawn as display formula, showing you the double bond, showing you the carbon with 4 single bonds, oxygen forming 2 covalent bonds, and each hydrogen just forming a single covalent bond. These are 1 molecule of ethanol, 3 molecules of oxygen, 2 molecules of carbon dioxide, CO2, where each carbon form 1, 2, 3, and 4 covalent bond, and each oxygen forming 2 covalent bond like that. This is H2O, oxygen forming 2 covalent bonds, hydrogen forming 1 covalent bond each. Use the bond energies in order to calculate energy change. This has to be in kilojoule per mole. For the complete combustion of ethanol, complete combustion of ethanol will give you CO2 and H2O. According to the equation here, we're going to count what bonds are being broken. If we look at the energy needed to break the bonds, these are of the reactants, because the reactants have to, break all the bonds. For combustion, what we have is one-time carbon-carbon bond. And we have 1, 2, 3. If I draw it out, 1, 2, 3, 4, 5. There are 5 of these CH covalent bond. And then I have 1 of these CO covalent bond. I also have 1 of these CC, which I already written 1 times CC. So this is 1 times CO. And I have 1 time OH. And now I'm breaking 3 mole of this oxygen double bond. So looking at the table, I can say that 1 times 3, 4, 7 for the 1 times CC, 5 times 4, 1, 3 for the CH, 1 times 3, 5, 8 for the 1 times CO, 1 times the OH, and last but not least 3 times the 4, 9, 8 for the 3 times the oxygen double covalent bond there. These are all from the year 9 dot and cross formulations, and you just need to be able to press your calculator fairly quickly without making any mistake. I have gotten this as 4728 kilojoule because we already multiplied by the mole there, so it becomes kilojoule. So that's 4728. But just in case, because we never know how good we are at pressing your calculator, I'm just going to press my calculator all the way from scratch, not by going back, but by pressing 0, and I still get 4728 kilojoule there. In terms of the energy release when we form bonds, so these are of the products, so we're going to form whatever of the product. We have 2 times C double bond O, but we got 2 times CO2, so altogether 4 times C double bond O total. So in one molecule, you have got 2 times C double bond O, but you're forming 2 molecules of it, such that you will get like this, and if you count, you will see 1, 2, 3, and 4 of this CO double covalent bond. So I'm just going to cancel that thing there because now you can see there are 2 of it. 3 water molecules. So I'm going to draw it out so that things are very, very clear to me. 3 H2O means 3 of these. So there are 6 times OH and 4 times C double bond O. So I'm forming 4 times C double bond O, and also 6 times the OH. So 4 times the 805 for the C double bond O, and then 6 times the OH. So 6 times 464 for the 3 water molecule. So 4 times 805 plus 4 times 805 plus 6 times 464, I get 6004 kilojoule. But as with our calculation, let me just check again. I've got 4 of this C double bond O, so 805 times 4. And then I added with 3 of these H2O molecules, which give me 6 OH bonds, so 6 times plus 6 times 464, and I still get 6004 kilojoule there. Now energy change for the complete combustion, so we know enthalpy change is to do with the sum of energy for breaking bond minus the sum of energy for forming bond. And then these are the sum of energy. So breaking bond 4728 kilojoule minus 6004 kilojoule. Actually, that one is actually energy difference. And 4728 minus 6004, my calculator gave me minus 1276 kilojoule. If you see here, kilojoule per mole is actually enthalpy change. It's going to be the energy change divided by the mole. Mole of what? Mole of the ethanol. If we look at the equation, we have 1 mole of the ethanol. So whatever energy change we had earlier is going to be divided for 1 mole of ethanol combusting completely. So this is just dividing it by 1, which is basically itself. So dividing it by 1, which is going to give me minus 1276 kilojoule per mole. So it has a sign, a value, and a unit. A sign, a negative sign indicating it is exothermic, because combustion is always exothermic. Combustion is never endothermic. Combustion is always exothermic. It releases heat energy to the surroundings, and the surrounding will get hotter as you combust ethanol there. This next bit ethene gas. Ethene is actually part of your dot and cross in year 9 covalent bonding. It was in the dot and cross together with the name of the molecule. Characteristic is this carbon-carbon double bond because carbon form 1, 2, 3, and 4 covalent bonds. This carbon also form 1, 2, 3, and 4 covalent bonds, and each hydrogen only form a single covalent bond. C2H4 is ethene. You can of course draw the dot and cross from what I've shown you there. So that is a double covalent bond. So each carbon contributes 2 electrons, and the other carbon contributes the other 2 electrons. And then dot cross hydrogen for the single bond to the hydrogen there. So ethene dot and cross, year 9 covalent bonding, and you will learn more about ethene in organic chemistry. This question, however, is not about organic chemistry. It reacts with steam in order to give you ethanol. You can see the equation is balanced. These are gas, gas, and also gas. This question is about equilibrium, reversible changes under dynamic equilibrium. That is when the rate of forward reaction going from left to right, reactants to products, forward reaction, the rate of forward reaction equal to the rate of backward reaction. That is one idea of dynamic equilibrium. The other one is that the concentration of the reactants and the products are no longer changing. They told you here the forward reaction is exothermic. So what is the effect of increasing the pressure? First of all, pressure affect gases. So pressure affect gases. When we talk about the position of the equilibrium, so this is about the equilibrium yield, equilibrium position. We really need to think about not about how fast, but about counting the moles of gases on both sides. So there are 2 moles of gases on the left. There are 1 mole of ethene, and then there is 1 mole of steam. So 1 mole and 1 mole, gas and gas. So 2 moles of gases on the left side. And then there is only 1 mole of gas on the right side. So what happens is when pressure increases, when we increase pressure, Le Chatelier principle says that the equilibrium will try to oppose the change. So the system, or you can say the equilibrium, will try to decrease the pressure that is opposing the change. And how would it do that? Well, the side with the lesser gases are the right side. Lesser gases mean lesser molecules of gases. Lesser molecule of gases will exert lesser pressure because lesser molecules hit on the walls of the container, so lower pressure. If you try to decrease pressure, you will shift to the side with lesser gaseous molecules. And when we go back to our first statement, the side with the lesser gaseous molecules will be on the right side since we already counted the moles of gases. Therefore, what is the effect of increasing pressure on the position equilibrium? Therefore, equilibrium will shift to the right-hand side. Therefore, favor the forward reaction, favors the right side, or equilibrium shift to the right, favoring forward reaction. It's actually not asking you on the yield, so perhaps I can cancel out equilibrium yield since that is not what it's asking. It's asking on the position there. Part 2, increasing the pressure increases its concentration. So what is the effect? State and explain the effect of increasing pressure, which is the same as increasing concentration on the rate of reaction. This is to do with how fast, not how much. So do not focus on the equilibrium. Instead, we got to think about collision frequency. So what happened at higher pressure? We will have more gaseous molecules. So there are more gaseous molecules per unit. There are more gaseous particles or more gaseous molecules. If you want, you can use the word particles. And this is per unit volume since the concentration increases, because according to the question, concentration is in mole per dm cube. So since concentration increases as pressure increases, therefore, since there are more gaseous molecules per unit volume, they collide more frequently. The reacting particles collide more frequently. The reacting particles collide more frequently. The reacting particles collide more frequently. I don't know how many times I have repeated that. And we relate collision frequency to the effective collision So we can say more effective collision. But we still haven't answered the question. The question is really asking you on the state, what happened to the rate. So therefore, rate will be faster. Rate is higher, so rate increases. So rate become faster or rate increases there. Last but not least, we have state and explained the effect of temperature increasing on the position of the equilibrium. Again, this is Le Chatelier principle. We always start off the essay with temperature and equilibrium position by stating what happened to the forward reaction enthalpy change. That was already given the question. The forward reaction is exothermic. So exothermic would mean that the forward reaction releases heat to the surrounding. So what happens when temperature increases? Well, the system or the equilibrium will try to oppose the change in order to go back to being equilibrium. So I can say the system or the equilibrium will try to decrease the temperature because it want to oppose the change, so decrease temperature. And how would it decrease the temperature? If you look back at your first statement saying the forward reaction release heat energy to the surrounding. If you want to make the surrounding cooler, so you will release lesser heat energy to the surrounding by releasing lesser heat to the surroundings. But we also know the forward reaction release heat to the surrounding. If we release lesser heat to the surrounding, therefore the equilibrium will shift to the backward, it will shift to the left hand side. So equilibrium shift to the left. Equilibrium will favor backward reaction. They haven't asked you on the yield, but if they do, then you can establish that there will be lesser yield of product because it will favor the backward reaction, backward side. Equilibrium shift to the left, that is on the position equilibrium. That is what this question is asking for, and that's it really overall for this 9 marks question. That's it really overall for this paper 2 for the year 10 end of year assessment. This year 10 are doing the 3-year curriculum, and as such the O-level contents, which are similar to IGCSE or GCSE pure chemistry triple sciences curriculum for 14 to 16 years old students all around the world, are pretty similar, with the exception that environmental chemistry and organic chemistry have not been included because those are year 11 topics in the 3-year curriculum. But this paper is pretty complete on its own, and it has assessed almost every other single topics. Thank you for watching. Don't forget to click the button on the bottom right to subscribe to my channel. Do follow me at ptet.chemistry. That's at ptet.chemistry on Instagram, Facebook, Twitter, and Telegram to get connected. I'll see you in the next tutorial video. Thank you for watching again.